Greetings and welcome to All Things Physics, where we examine all kinds of interesting things using the lens of science. Today, I want to circle back to a previous video where I showed that a ball being swung around in circular motion on a string will continue moving in circular motion for a short time after the string is released. If you haven't already seen it, it's probably a good idea to watch that video before continuing. As a quick reminder, the previous video asserts that when the string is released, it takes a finite amount of time for the tension wave to travel through the string and reach the object. Thus, the tension continues to act for a short amount of time after the string is released, which means the object continues its circular trajectory for a short amount of time. This phenomenon was demonstrated using a slinky, a rubber noodle, and an elastic cord. Unfortunately, we were unable to capture this effect on video using an actual string because the tension wave simply travels too fast. I was pleased to see that a lot of people agreed that this phenomenon is truly mind-blowing. On the other hand, a good number of you thought I was asking a trick question and complained that the video was simply clickbait. Clickbait? Really? In any event, the thing that surprised me the most was the number of people who said I did the wrong experiment and should have cut the string right where it's attached to the ball. So, in today's video, we're going to take a closer look at circular motion and a ball being swung around on a string. Among other things, we'll see that there's no centripetal force acting in this problem. That's right, none of the forces acting in this problem are centripetal. Now, before getting started, there's an important point from the previous video that needs some clarification. A couple of viewers brought up a very insightful point, asserting that my conclusion about where the ball lands after being released is flawed. Recall that I stated that the actual landing spot would be more than 12 centimeters from the traditional landing spot when the ball is assumed to instantly travel tangent to its circular trajectory. Their argument is that immediately after releasing the string, the center of mass of the ball string system should move off in straight line motion and will therefore end up much closer to the traditional landing spot compared to what I claimed in the previous video. This is an excellent point and one that I emphasized in the previous video when discussing the surprising behavior of a dropped slinky. However, we need to remember that it's only true if there are no external forces acting on the system. And while it might be reasonable to assume that air drag on the ball is negligible, it's definitely not reasonable to assume that air drag on the string is negligible. In fact, the string will lose energy by doing work on the air and will therefore impart significantly less momentum to the ball than it would in the absence of air drag. Now, it's true that my previous answer assumes that all of the string's energy is lost to the air, and this is unlikely to be the case. But it's definitely not the case that none of the string's energy is lost to the air. The real answer, of course, will lie somewhere between these two extremes. Precisely where the true answer lies is difficult to determine. But based on the non-negligible interaction between the string and air, I suspect the true answer will lie somewhat closer to my original answer. Let's now turn our attention to an object that's moving in uniform circular motion, which means it moves in circular motion with a constant speed. For now, let's not worry about what's causing it to move this way. Let's just focus our attention on the actual motion. Although the object moves with a constant speed, it should be clear that the direction it moves is constantly changing. Because velocity is a vector, incorporating both speed and direction, this changing velocity tells us that the object is accelerating. To determine the acceleration in this situation, we examine how the velocity changes in a small time interval. One thing we notice right away is that the change in velocity, and therefore the acceleration, is perpendicular to the velocity vector, pointing directly toward the center of the circle. We can find the magnitude of the acceleration by taking the magnitude of the velocity change and dividing by the time interval. Shrinking the time interval to 0 then leads to an expression for the acceleration magnitude. Because the acceleration always points to the center of the circle, we call this a centripetal acceleration, the word centripetal meaning center-seeking. In vector form, the centripetal acceleration can be written in terms of the inward-pointing unit normal vector. It's worth emphasizing this result one more time. We have just shown that when an object moves in uniform circular motion, we immediately know that its acceleration points toward the center of the circle and has a magnitude of v squared over r. This is a powerful result that turns out to be extremely useful. Before moving on, it's worth pointing out that this result can be generalized for an object that moves along an arbitrary curve with a changing speed. Here's an example of a non-circular path and an object that has a velocity with a changing magnitude. We write the velocity vector in terms of the unit tangent vector and then differentiate to find the acceleration. Using the chain rule, we end up with two terms. The first is a result of changes in the object's speed, while the second is a result of changes in the object's direction. But we just derived a formula for the acceleration due to a change in direction. That's just the centripetal acceleration. Thus, we find that in the general case, the acceleration has a tangential component, given by the change in speed with respect to time, and a normal component with magnitude v squared over r. The only problem with this expression is identifying what the quantity r physically represents. Remember, we're no longer assuming the object moves in circular motion, so the trajectory doesn't have a fixed radius. However, the trajectory can be thought of as having a different radius at each point along the trajectory. We call this the radius of curvature, and it's equal to the radius of the circle that's both tangent to the curve and has the same curvature at the point of interest. Such a circle is known as an osculating circle. Thus, the quantity r represents the radius of the osculating circle at each point along the trajectory. Qualitatively, you can think of the object as instantaneously moving in circular motion about the center of the osculating circle, which itself is continually changing in time. To see how this relates to acceleration, let's consider once again the motion of an object along the non-circular trajectory we've been considering. This path happens to be a cycloid, the solution to the famous brachistochrone problem, which minimizes the time when sliding between 2 points under the influence of gravity alone. Here, we see that the acceleration vector, shown in red, has components both tangent and normal to the trajectory. As just discussed, the tangent component is the rate of change of speed, while the normal component is v squared over r. Let's now return to the topic of uniform circular motion and see how it applies to a real-world situation. As we've seen, for uniform circular motion, the acceleration points toward the center of the circle and has a magnitude of v squared over r. Therefore, whenever we're dealing with uniform circular motion, we can immediately substitute this acceleration into Newton's second law. In essence, then, all we need to do is sum the forces and set it equal to the mass times the centripetal acceleration. Let's see how this plays out in a simple experiment. The experiment we're going to do is pretty simple. I've got a plexiglass cylinder and a couple of steel balls. And when you roll the ball inside the cylinder, no surprise, it moves around in nearly uniform circular motion. Now, if we flip the cylinder over, we've got a notch cut in it, so the ball will then get released. If we film the whole thing from above, Then we can see exactly what the trajectory of the ball looks like. Here's the motion of the ball when viewed from above. Of course, in any real experiment, there's going to be friction, air drag, and rolling resistance. But these are minor effects that we're going to ignore. With these assumptions, the ball moves in uniform circular motion, so let's apply Newton's second law in the horizontal direction. We start by examining the forces acting on the ball. Neglecting friction and air forces, there's only one horizontal force acting, the normal force from the cylinder. This force acts perpendicular to the cylinder and therefore points directly to the center of the circle. Because the ball moves in uniform circular motion, we already know the acceleration also points toward the center of the circle. Substituting into Newton's second law then allows us to determine the magnitude of the normal force acting on the ball. Notice that in this situation, there's only a single force acting, and this force is sometimes referred to as the centripetal force. Unfortunately, this terminology can be very misleading and causes all kinds of confusion, especially in situations where there are multiple forces acting. Personally, I think it's best to avoid this term altogether. I'll return to this point shortly when we analyze a more complex problem. But first, let's see what happens when we flip the cylinder over. Recall that there's a notch cut out of the cylinder on the other side, so when I flip it over, I'll orient the notch to begin at 12 o'clock. Thus, when the ball is rolled inside the cylinder, it will experience a force that instantly disappears. This is analogous to swinging a ball around on a string and cutting the string right where it attaches to the ball. Let's see what happens. Notice that the ball moves along a straight line the instant the normal force disappears. This makes sense when you consider that once the force from the cylinder is gone, there are no horizontal forces acting on the ball. Thus, by Newton's first law, the ball should move with a constant velocity. In reality, of course, the ball slows down slightly due to friction and rolling resistance, but it should be very clear that it moves off tangent to the original trajectory. I'd like to now consider the ball on a string problem from the previous video. Viewed from above, and again neglecting air resistance, this problem appears to be two-dimensional and essentially identical to the ball rolling inside the cylinder. The only difference is that the force acting on the ball is now a tension force from the string instead of a normal force from the cylinder. But the solution proceeds in an identical manner. One interesting thing to investigate in this problem is how quickly we can twirl the ball around before the string breaks. Given a maximum force for the string, it's not difficult to solve for the rotation rate as a function of this maximum force. Notice that this rotation rate decreases if we increase the mass of the ball or the radius of the circle. If you've ever played around twirling a ball on a string, this fact probably won't be too surprising. Although this is a standard textbook problem in physics, it's worth pointing out that there's a hidden assumption in this problem, which becomes evident if we look at the situation from the side. From this perspective, it becomes clear that the string, and therefore the tension force, is not horizontal. Moreover, unless we can somehow eliminate the effect of gravity, it's impossible to make the string horizontal, no matter how fast you twirl the ball around. Let's take a look from a 3D perspective. One thing we notice immediately is that the tension force does not point toward the center of the circle. In other words, the tension force is not a centripetal force. The only other force being considered is gravity, which also does not point toward the center of the circle. Thus, in terms of the forces acting in this problem, there is no centripetal force. Of course, if the ball is moving in uniform circular motion, then we know the acceleration must point toward the center of the circle, which means it's the net force that points toward the center of the circle. In other words, the net force is the centripetal force that keeps the ball moving in uniform circular motion. But notice that the net force here is not a single force in the sense that we would add it to a free body diagram. And this is why I dislike the term centripetal force. It's too easy to think that the centripetal force should be included in the free body diagram as a separate force, and this leads to problems. The bottom line is that the term centripetal force is entirely unnecessary, and all it does is add confusion. So, for these reasons, I recommend avoiding this term altogether. The string on a ball problem is an example of what's referred to as a conical pendulum, so named because the string traces out a cone as the ball moves around in circular motion. A natural question we might want to ask about this problem is how the cone angle depends on the rotation rate. To figure this out, we apply Newton's second law in the horizontal and vertical directions, and then eliminate the tension force to give us a single equation in which we can solve for the angle. To see if our solution makes sense, let's consider some limiting cases. As omega gets large, the cosine term must approach 0, which means the ball twirls around in a horizontal plane, exactly as we'd expect. But what happens when omega goes to 0? Now the right side of our equation goes to infinity, whereas we know the cosine function is bounded by 1. Thus, the only way to have a solution is for the right side to be less than or equal to 1. Incorporating this constraint, we find that the rotation rate must have a minimum value that happens to be equal to the angular frequency of a simple pendulum in the small angle limit. Initially, I found this result to be somewhat surprising. We can gain some insight into this behavior by playing around with a conical pendulum. If we pull the mass to the side and release it, we end up with a simple pendulum, which we will assume oscillates in the x direction. If we now pull the mass aside again, but this time we give it just the right velocity in the y direction, we see that the ball traces out a circle and we have a conical pendulum. However, we know that what happens in the x and y directions are independent of each other, so the conical pendulum must still be oscillating in the x direction in precisely the same way as when there was 0 initial velocity. We can therefore conclude that a conical pendulum has the same period as a simple pendulum with the same initial angle. Moreover, this fact is true for all angles, not just for small angles. If we push this idea a little further, we find that a conical pendulum is nothing more than a simple pendulum in the x direction and a simple pendulum in the y direction that has the same length but is 90 degrees out of phase with the first one. This is a very nice way of understanding a conical pendulum, and in hindsight, it seems like it should have been more obvious at the outset. Recall that our earlier analysis led to a concrete prediction for the cone angle as a function of rotation rate for a conical pendulum. Thus, it seemed silly not to perform a simple experiment to test this prediction. Therefore, we recorded slow-motion video of the pendulum at different rotation speeds and then analyzed the video to measure the angles. Let's take a look at the results. As you can clearly see, the experimental results agree quite nicely with the prediction, making this a nice project for student exploration. So there you have it. Everything you always wanted to know about circular motion and more. And if you happen to teach physics, do your students a favor and stop using the term centripetal force. And with that, I'll bring this video to a close. I'm David Jackson, and this is All Things Physics.